Okay, so today I'm very excited because I'm going to be talking about something that I like much, I like a lot, and it's body plot. So what's body plot? Why do we bother with body plots? Well, let first thing first. Let's suppose that if you come here, if you're here, it means that you already know about Laplace transform and other kind of transform. So you are already familiar with the Laplace transform, and you basically know, okay, whenever we are dealing with something really complex and has the dependency is time dependent, then we can bring it into the frequency domain, solve it for the frequency domain, and then go back and check the result. Now, one thing that is very, very important once we have got the transformation, we are in the frequency domain, so we're not dealing with t anymore, we're dealing with s, is to represent what we have just found. And we can do that thanks to the body plot. The body plot is really interesting. We can actually say, well, what if we don't treat what we have just found in terms of as a function? Well, we can't because it would with complex numbers we will require a four-dimensional plane, which is not something we can represent, at least not in with pen and paper. So there are any sort of tricks like a Riemann surface and so on, but I'm not going to be talking about Riemann surface. So today we're going to be focusing on the body plot. So let's suppose that we have our h of s with these function here. So s plus 1 over s plus 10 times s plus 100. Now, what I'm going to do in order to represent this, I'm going to do one quick thing before I start, and is to normalize it. So why do I normalize? Why do I bother with that? Well, because it's easier than to plot and to analyze. So by normalizing it, I mean that I want to get rid of these 10 here and these 100 here because I want to have just s over something plus 1 because it's way easier this way. So, and you can always do that, technically. So what I'm going to do, I'm going to say, okay, I'm going to say 100 times, I'm going to still have s plus 1, but here, notice that I want to get rid of this 10, so multiply by 10, so 10 times s over 10 plus 1 times, I'm going to have, when I get rid of this 100, so I'm going to have s over 100 plus 1, and of course I had to multiply by 100. Oh yeah, let me just do a quick correction with 1000 because otherwise I'm not gonna have those two. So what do we do now? Well, 10 times 100 gets 1000. So this 1000 is simplified with this 1000. And what do I get? Well, I get just this. I get s plus 1 over 1 plus s over 10 times 1 plus s over 100. Okay, now what I'm gonna do is to set, I'm basically gonna set s equal to I omega. You may find j omega according to your text for the reason that I've been talking about extensively several other times, because they just say, well, the highs can be confused with the current, but it's not because it's lowercase, so I don't, anyway. So we set s equal to I omega. So what do we have? Well, in this case, we're going to have an age, not anymore in terms of s, but in terms of I omega, which is essentially 1 plus I omega over 1 plus I omega over 10 times 1 plus I omega over 100. So this one at the top, okay, so this one, the numerator, is called a zero of the function. And those at the bottom are called poles. Well, this is just pole, those two are poles. Now, we're going to be dealing with them individually. So we're going to deal with 0 and with the 2 poles individually. And then we're going to plot everything. And what we're going to plot is going to be the gain and the phase. Let's start with the gain. Now, what I'm going to do is that I'm going to bring those three, so basically the 0 and poles, in decibel, because the scale in which we're going to represent them is going to be in decibel. And I'm gonna analyze them individually. So how do we bring something in decibel? Well, we just say, okay, it's 20 times something to bring something in decibel. So let me just say, okay, we're gonna deal with the 0, and then we're gonna do with we are gonna deal sorry, with the poles. So whenever you have a 0, it's always gonna be positive. Okay, so you don't add anything in front of it. Whenever you deal with the poles, we're gonna have to add a negative sign in front of it. The reason for that, it's I could explain that, but I'm not gonna explain it anyway right now anyway. But because some people don't just deal with them individually, but it would deal with them all at once. And so whenever they bring them into log, so into decibel, basically this division basically becomes a subtraction. So this is why you have a negative sign. But anyway, I strongly suggest you to do it my way. Well, I didn't invent it, but anyways, is what the professor actually taught me back in the day, which is to deal with them individually. It's going to be really easier. So let's deal with the first one. So with the 0, with a numerator, we just call it 0. I'm going to call it 0 and pole, and the denominator as poles from now on. So a 0, I'm going to have 20 times log of the norm, the Euclidean norm, type 2 norm of this one, so 1 plus I omega. So the Euclidean norm, well, we still gonna have 20 times log of, if I remember the video about the norm of a complex number, it's just the square root of d squared plus d squared without the imaginary component. So it's just 1 squared plus omega squared. So, well, let me just rewrite this. So 20 times log of the square root of 1 plus omega squared. Now, if I'm gonna say two things. If omega is equal to 0, then we're going to have 20 times log of the square root of 1, which is just 20 times log of 1, because the square root of 1 is 1. But log of 1 is just 0, so 20 times 0 is just 0. Now, if omega is way greater than 1, then we're essentially going to have just this number here. It's just like setting it, doing a limit, setting this to infinity. If we have 1 plus infinity, it's just going to be infinity. So it's just like saying, okay, just like saying 20 times log of omega. Now, we're ready to sketch our first graph for the game. And our first graph is going to look like this on a logarithmic scale. So we're going to have 1 here. And essentially what it's going to do is that whenever you have a 0, if it's positive, it's going to go up. If it's negative, it's going to go down. Whenever you have a pole, if it's positive, it's going to go down. If it's negative, it's going to go up. So basically, whenever you have a 0, it goes up. Whenever you have a pole, it goes down. So it's 0, and therefore it goes up, just like this. So therefore, our function will look essentially like stationary, like till 1, and then it's going to go up. So it's not over, we're just barely getting started. So now what we're going to do is that we're going to have to deal with the poles. So how do we do that? Well, we do the exact same thing we have been doing for the 0 for each individual pole. Except for the fact that we're going to have a negative in front of everything when we do 20 times log of the pole to bring it into decibel. So let's do that. Let's deal with the first pole, so this one. So if we bring that into decibel, we're going to have negative because it's a pole, so pole have negative sign in front of everything, times log of the module, so the norm, the Euclidean norm, type 2 norm of 1 plus I omega over 10. Now, again, if you remembered about, oh, yeah, I should be closing it. Okay, so if you remember about the Euclidean norm of this logarithm, you're basically going to have the negative 20 times log of the square root of the first square plus the second square. So 1 square plus I omega over 10 squared. Now, this is just, I'm just going to do it 100. Well, no, I'm just going to leave it this way. It's fine. Well, yeah, let me just do negative 20 times log of square root of 1 plus, I'm going to leave this alone, so I omega over 10 squared. Oh, shoot. Yeah, I was including the imaginary part. No, I shouldn't. I shouldn't. Okay. So, yeah, let me just correct this. Whoops. Okay. I corrected it even in my notes as well. Okay, so what do we do now? Well, we do the same thing we have been doing for the 0. So we're going to say if and if. But in this case, we're going to our breakpoint. Well, and it's not going to be called a breakpoint, but our what we're interested in is no longer 1 as it was for this one, but it's going to be 10 because when, well, let's just do this. Okay, negative 20 times log of square root of 1 plus omega square omega over 10 everything squared. Okay, now if we say the exact same thing, we're going to have if omega is way lower than 10, then what do we have? Well, omega is way lower than 10, okay? So basically we have something really really small divided by something hugely big. So this is basically 0. This term, this whole term is 0. It's like setting these to negative infinity, this one to 10. Negative infinity is something really, really small, and divided by something really, really big is just gonna be 0. So we essentially would have negative 20 times log of the square root of 1. But again, this means that we have negative 20 times log of 1, which is essentially negative 20 times 0, which is 0. So again, now we're going to say, okay, fair enough. Now, what if omega is way greater than 10? So we're going to have this one really, really, really huge, like going up to infinity, divided by something that has now become relatively small. Then this divided by this is still going to be like infinity, something really, really big. Plus 1, what do you think 1 is going to do? Nothing. It's just going to be, something really, really big. So it's like saying negative 20 times log of omega. Which in this case, well, I was almost making a mistake. So it's like saying negative 20 times log of omega plus 20 times log of 10. So in this case, when we plot our graph, we're basically going to have this one. I'm just gonna try to do it on scale. So if I just put 1 here, then 10 is gonna be here. And since it's a pole, it's gonna go down. So it's gonna be steady till here at 10, and then at 10 is gonna go down. So it will be like, it will go like this. And this one should really be here on top of the blue one, but I'm not gonna, I can't really do one on top of the other. You wouldn't see it anyway. So let's turn the page and go on. Now, what's left? Well, at least for the game, for the first part, we still have to deal with these other poles. So the 1 plus I omega over 100. But it's essentially going to be the same, because we're still going to have, okay, it's pole, so it's negative 20 times log of the pole, which is 1 plus I omega over 100. Oh, the norm of this one, just like before. So the norm of this one will be negative 20 times log of the square root of 1 squared plus omega over 10 over 100, I'm sorry, squared. So we'll just say it's negative 20 times log of the square root of 1 plus, I'm going to leave this alone, so omega over 100 squared. And again, I'm going to correct one more thing in my notes. Anyway, so now we're going to do the exact same thing that we did before. We're just going to say, okay, what if omega is less or bigger and so on, and then we're going to plot it. Because we're interested in when it's 0 and when it's not 0. So I'm going to say, okay, 20 times log of square root of 1 plus omega over 100 squared. Okay, if omega is way less than 100, then we're going to have negative 20 times log of the square root. It's just like saying, okay, it's way less than 100, just like before. So it's going to be a really, 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 really small number divided by something huge. So it's essentially going to be 0. So we're still going to have the square root of 1. So this means it's negative 20 times log of 1 but the logos 1 is 0, so it's negative 20 times 0, so it's essentially 0. Again, nothing surprising. But now, if omega is way greater than 100, what do we have? Well, again, we're going to have something huge divided by something that is now become relatively small. So it's still going to be something huge. Then we're going to add 1 to this, which is not going to make any difference at all because 1 is such a small number. So I'm going to have negative 20 times log of omega plus 20 times log of 100. So now we can plot this as well. And our Bode plot for this is, well, we had 1 approximately here, 10 approximately here, and just say that 100 is like here. And again is, as I said, it's a pole. So 0 go up, the zeros go up in the numerator, and the poles at the denominator go down. So since this one is a pole, it's going to go down. So it goes down, just like this. So it would have something like, which is essentially like this, and then it goes down. Now, is it over? No, it's not, for two main reasons. The first reason is that we have to actually sum the contributes. So each of these things that we have found was relatively easy, but was just the individual one. So this individual 0, this individual pole, and the other individual pole. Now we have to add all of them and see what the resulting graph is. And doing this is called the superposition. We've already been talking about superposition in the past for completely different things, but I told you that it was going to be very and extremely useful for many other things. And it's one of the things it is used for. So now I'm going, this G is horrible. I'm not going to be able to sleep tonight. That's just okay. So I'm going to add all the contributions. Now, we're still going to have our graph, but this is going to be our final Bode plot. So, this is 0. What did we have? Well, we have 1 here. So in the first one, nothing happens till 1. In the second one, nothing happens till 10. And in the third one, nothing happens till 100. So we all agree that for all of those, so this one, and this one, nothing happens till 1. Because, you know, here nothing happens till 10. And in the other page here, nothing happens till 100. So essentially, if I have just, you know, if I go to 1, I can safely walk through 1 and nothing is going to happen. So this is going to be my 1 and nothing is going to happen. Now, what happens next? Well, let's see. I'm going to have 10 here and 100 here. Now, what happens next? Well, essentially, from 1, we are basically going to go up because the contribution of this one between 1 and 10 is nothing, and the contribution of this one between 1 and 10 is nothing. Because it starts from 100 and this other one starts from 10. So essentially we're going to go up till 10. So we are going to go up till 10. Let me just, there we go. Now what happens at 10? Well, these poor little function here, which is given by our 0, wants to go up. However, as soon as 10 kicks in, we're going to have this pole that brings us down. So what do we do? What happened when we have those? Well, we'll have something that wants to go up, something that wants to go down. So they're gonna, they're gonna go one against the other, and we're gonna go flat. So essentially, from here, we are going to go flat. Now, what happens when we reach 100? Well, when we reach 100, we have this one that kicks in and is a pole that wants to go down. So again, one can no longer, fight against 10 and be flat, because 100 is gonna kick in and it's gonna bring everything down. So we're essentially gonna go down, 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 all the way to infinity, because it's nothing is gonna stop this big fat guy from bringing everything down. So yeah, this is essentially our body plot. And it's you're gonna whoa. I didn't actually say, well, there is a scale. There's a reason why I have been drawing this like this, and this one is 20 times log of 10, which is basically equal to let me just say 40 dB, because it's in decibel. It's a logarithmic scale in decibel. So yeah, but yeah, this is pretty much it. So yeah, this is essentially our body plot. Thanks for watching.